Welcome to this video on design for life cycle towards sustainable aviation. In the previous section, you learned about the 4 life cycles of aircraft. Here, I will present sustainability considerations related to the design phase of an aircraft. Minor environmental impacts are expected in this phase from research and development and market exploration. You can think of designing and creating new materials and machines required for specimen production and testing and the resulting energy demand and waste. But also consider flights and transport of aircraft manufacturers' employees to visit potential customers to understand their needs, or energy and computers required for regular online meetings. A larger environmental impact is coming from energy needed to power the high-performance computers and servers to perform calculations on flight physics and aerodynamics, digital detailed designs, virtual reality for enhanced customer experience, and so on. But in this section, you will mainly learn about one very important design aspect for sustainable aviation: weight, and how we can reduce it. In the module on the basics of flight, you learned that there are 4 forces at play that keep an aircraft flying: lift, thrust, drag, and weight, also called gravitational force. The forces lift and drag are a result of aerodynamic design, which is part of another module. Thrust is directly related to propulsion and is discussed elsewhere. As mentioned, here we will focus on weight, which is defined as the gravitational constant times the mass. Often the word weight is used where actually mass is meant. We will try and focus on mass in this lecture. When you consider that for every kilogram of saved mass, roughly 120 kilograms less fuel is burned per year, then it becomes clear that mass reduction is of significant importance to reduce emissions for flying. And if there is less mass to bring into the air, the engines can be made lighter, less fuel needs to be carried, and so on and so on. So, how can we reduce the mass? Engines, the structure, interior, and systems, they are all made of materials that contribute to the total mass. Therefore, it makes sense to look into the materials selected for aircraft components and the decision drivers. Sustainable materials are selected based on the following criteria. Material properties, they include mechanical properties such as strength, environmental resistance, for example temperature resistance and fluid resistance, fire properties, and density. Design criteria, they are about tolerances. Can the material be formed into specific design features? Does it have potential for a lightweight design? Can the material fulfill multiple functions such as fire retardation and mechanical strength at once? Life cycle criteria are based on the other life cycle phases. About manufacturability, reproducibility, repair options, option for disassembly for end of life, recyclability, compatibility with paints and adhesives, and so on. Supply chain requirements include: are there sufficient test data available and data for LCA? The price: is there a responsible and resilient supply chain? Health, environment, and safety requirements are, for example, that you are not allowed to use hazardous substances or substances of concern. They shall not be used during mining and production. And of course, the materials shall have a low environmental impact as assessed with a life cycle assessment. You can read about the common materials used in aircraft and their properties in this lecture's material. Today, a single-aisle aircraft, such as the Boeing 737 and Airbus A320, consists roughly of 80 weight% aluminium alloy, 10% titanium, 5% steel, 3 weight% composites, and 2% other materials. The big super jumbo Airbus A380 entered service in 2007 and is suited for many passengers on long-haul flights. It has 61% aluminium, 22% composites, 5 weight% steel, 5 weight% titanium, and 7 weight% other materials, such as fiber metal laminates. The newer Boeing 787 Dreamliner that entered service in 2011 for intercontinental flights consists of 50% of composites, 20% aluminium, 15% titanium, 10% steel and 5% other materials. So what we can learn from this is that long-haul and newer aircraft use more composites for a lighter material selection. The cost saved by lower fuel burn compensates for the higher cost of composites. I want to recall especially the importance of material selection on the mass or weight of an aircraft. For example, lightweight composites were first introduced in the Airbus A300 in 1972 to reduce the mass. More recently, the change from aluminium in a Boeing 767 to composites in a Boeing 787 resulted in a 20% mass reduction for the structure. Actually, the first aircraft was also made of composites, with a textile fabric impregnated with a polymer resin. And wood itself is a composite consisting of cellulose and lignin. But what is most important is to remember that any design decision, such as material selection, has an impact on the entire life cycle. To use the example of Glare, a fiber metal laminate that was developed at the TU Delft. This material was selected to make an Airbus A380 800 kilograms lighter, which had a cascading effect towards a total of 1,300 kilograms saved for lighter engines, lighter wings, less fuel, and so on. However, since this material is composed of alternating aluminium sheets and glass fiber reinforced epoxy, the total energy required for production is higher when compared to single aluminium. It is more difficult to repair in operations, and it is more challenging to recycle the material due to the material's mixture, not to mention the higher cost. But this is all worth it in terms of weight saving during operations. So, material selection has a large impact on design, manufacturing and end of life. Let's see how in the following lectures with Irene Fernandez Villegas. This is all from me for now. I thank you for your attention. Bye.